Hi, I'm Marisa, and I will talk about the connection between neural network, functional programming, and programming language. So the main idea of the talk is neural network are program, and by seeing them as such, we can use programming language technique or functional programming language technique to help us build better neural network and help us understand neural network. But why? Well, neural networks are really great, but it's hard to write a library for writing neural network, and they're called deep learning framework. So for example, in TensorFlow, a deep learning framework, it takes 200 lines of code to write scan for list. And another reason is by using programming language technique, like partial evaluation or automatic parallelization, we can make neural network run faster, as is the case with TensorFlow Fold. So what is a neural network? It is just a program, and we use a neural network by running the program. But it's a special kind of program in that it contains implicit parameter called weight of type double. The test of deep learning is to try to find the best weight, but how? So for each weight, so suppose we have a function that as input takes some weight and output a score for how good the weight for neural network is. What we can do is, for every weight, we will modify it in the direction that will increase the function, and we will repeat modifying it and until it is in a local maxima. This process is called gradient descent. And here is an example of why we should see a neural network as a functional program. So this is a recurrent neural network, and it can take a list of input. It's mostly used in natural language processing because a sentence is a list of tokens. Now, in functional programming language term, a recurrent neural network is just a fold. And here is a simplified convolutional neural network. And it's mostly used for computer vision. And in APL term, a convolutional neural network is just reduce on rotate. And in Haskell, we can implement it as a comonad zipper. Now we can think about how to actually train a neural network. So our train function takes a weight, a neural network, input and output as argument. It will then calculate the result. And it will compare the result to the output. And we will call that loss. Now, we'll get a derivative of loss with respect to the weight. And we will update our original weight with our derivative of loss. So the main question is, how do we find the derivative of loss? We can write that out by hand, but it's very hard and very tiring. So we want to find a computer program to write out the loss, to write out the derivative for ourselves. And before we begin, let's take a look at the roadmap. So I introduced what is a neural network. And now we want to find the derivative of the neural network so we can train it. And we'll start using a very simple form. And it's quadratic in the size of the input. So it's 1. And we want to optimize that. And then a neural network can take a lot of input instead of just 1. So we need to do the derivative of expression of a program with respect to multiple variables. And we need to optimize it again. Finally, we can implement a neural network. And in the end, I'm going to digress a little bit and talk about what it means to do automatic differentiation on higher order programming language. So the most simple thing we can do is we can use high school calculus rule to do program transformation. So we do pattern matching. So we do pattern matching on the program. And if x, we return 1. And pretty much the same for the following. And the list is not complete. Oh, thank you. And now the argument to the recursive call is simpler. So this rewriting process will always end. And the list is incomplete. I've omitted some rule, like the rule of minus, the rule of quotient, or trigonometry rule for brevity. But you can find them in your textbook. And here, we'll try to use string to solve for the equation. So we substitute weight with x. We substitute neural network with the equation with the left-hand side. We substitute output with the right-hand side. And we don't really have input, so it is a unit. And here's what we got. And if the result is greater than 27, d loss will be negative. No, d loss will be positive. And x minus d loss will decrease. And if result is less than 27, d loss is negative. And x will be increased. But it does not work. It's quadratic in this example. The reason is we call fx, gx, and hx trace. And we want to find a way to memorize the result to share it. Now looking back, we give an implementation of automatic differentiation. But it's quadratic, so we need to fix the problem. And then we can scale it to multiple variables and implement neural network. Now, the simple sharing strategy is we just share and memorize everything. So for every expression, we replace it with a tuple. And the left-hand side is the original expression. The right-hand side is a derivative of the left-hand side. And this is formally called a dual number. And this process is formally called a forward mode automatic differentiation, forward mode AD. And now it's linear time. So here is an example of how it works. Are you guys good? And here's how we can use forward mode AD on train. So basically, it's the same. But now remember, a neural network is a program. It's not a simple arithmetic expression. So we want to make a method work on program. The way we can do this is if the programming language construct is not related to view. So for example, if the construct is lambda application or lambda abstraction or just pattern matching on list, we'll just leave it unchanged. But if it's some operation related to view, we'll use the dual number version instead. And we can make it work on statically typed language. So suppose for the rest of the talk, that will work with simply typed lambda calculus. And we'll have product type, sum type, unit, void, and view. Now doing the derivative, we'll get us a term of another type. And we need to replace every occurrence of view in the type by a dual number, a type of view and a type of view times view. Now suppose we have a term f of view to view. If we transform it, we'll have a term of view time view to view to time view. This means give me an input of a dual number, with left hand side being some expression x, the right hand side being the derivative of x, and I shall return you a dual number, and the left hand side is fx, the right hand side is derivative of fx. Now let's look back. A crucial thing is we achieve the closure property. That means we can do derivative for every term in a language. And after we do derivative, we'll get a term in a language back, not a term in other language or a term in or a Haskell function. This means in addition to evaluating the term, we can do derivative again and again, so we get higher order derivative for free. Or we can do optimization on the result. And another thing is everything is typed. And with Finally Tagless, we can reflect the type of neural network back into the meta language, the Haskell. So when we compile a Haskell function, we can see if our neural network is well typed or not. Now by introducing prototype in our language, we fix the quadratic problem in our code. But a neural network has potentially many weights, so we need to make an approach work for multiple variables. And then we need to optimize it again, and we can implement neural network. Now let's look at all the dual number rule. So you can see that they follow a common pattern. So So the left-hand side of all the expression of all the two number is just itself. And the right-hand side is either 0, a plus, or a scaling with a real number. So that means we don't really have to store a real number in our right-hand side. We can store everything that has 0 plus or scaling. And that in mathematical term is called a vector space. Now, a lot of things is vector space. So, for example, a unit is a vector space, and it represents a neural network with no weight. We also have R, or prototype. So, if we want to represent a neural network with two real numbers, we'll use a tuple of view and view. And vector also have some algebraic law to them. So L plus R is the same as R plus L. 0 plus L is L plus 0 is L. And 0 scaling to R is 0. And L scaling 0 is 0 again. And here is a concrete example. So again, we transform everything into a dual number. And the left-hand side is the original expression. The left-hand side of the right-hand side is the left-hand side, is the derivative of the left-hand side with respect to x. And the right-hand side of the right-hand side is the derivative of left-hand side with respect to y. Again, we just use the dual number rule. Now, by generalizing gradient using type class or module or abstract data type, we can do derivative of multiple variables. Now we need to optimize it, so it's fast, so it can work for neural network with millions of variables, with millions of weight. After that, we can implement neural network. So why is it not good enough? Well, a neural network may have a lot of weight. So for example, 1 million of weight. And then it's expensive to do any operation on it. What we can do instead is we can represent the weight as we can represent the vector space as a closure. So it's a function from view to x, and the view is the scaling factor. And every time we scale, we just modify the scaling factor, and instead of looking into it and traversing the data structure. But now it's exponential. So the thing is, we need to make sure A, B, C is only called at most once. But we cannot do that since we cannot compare two functions. But we can compare AST. So instead of using closure, we will use AST. And then we can share AST and eliminate the exponential problem. So now our problem is we have a big data structure, but we do not want to use it directly. So instead, we can have some selector of that data structure, and it's called basis. So a basis of unit is void because there are no way to get a real number out of the basis. The basis of R is unit because there's exactly one way to get the real number out. The basis of a product type is a sum because we can go left or we can go right. And with basis, we can form a free vector, which goes from basis to real. But it's exponential because it's a function again. So we can represent it as a free vector builder, which is a map. And after we have done building the function, we can turn it into free vector by just indexing. Now we can represent the AST called a term algebra. The construction rule is exactly the same as the vector definition. But it also has a basis which let us take a value, which let us apply a value into the term vector. Now we can make a term vector into a F algebra by replacing all the recursive occurrence with a F, an additional parameter. Now we can get the original term vector back by calling term vector FB infinite amount of time. So it's like term vector FB of term vector FB of term vector FB. And that is called an isorecursive type. And we have unfold and unfold, which can like unfold or fold the data structure. And with data type a la carte, we can represent any algebraic data type. Now a term vector is a vector. We can just call the constructor. But in that example, we are still exponential because the size of the tree goes exponentially. But now a problem is simpler. We can share function, and we just need to use a DAG, a direct acyclic graph, to represent the AST. And we'll use a technique called hash consing. And the detail is in the paper shown above, and I won't go into detail. But basically, we can select this as the free vector space, as the vector space. And basically, what is a bimap of L and R is a map of L to R and a map of R to L. So it's a bidirectional map. And this is saying that is a vector, and this is saying that, wait.
Is B in term vector F supposed to be the other way around? Isn't the last parameter
The last parameter is the return of the state. So int is a pointer to the environment, and the environment is the bimap. So now our vector is a state which can look into the environment and modify the environment. And it will return an int, which is a pointer to the environment. And the environment is just store a lot of AST. But the child of the AST is not more tree. Instead, it's just pointer. So it forms a direct acyclic graph. But we need to convert it into a free vector of B. So we can start by inserting an empty bimap. That means we have nothing to begin with. And then we will get an environment back, and we'll have an int. And we can create a map of int to view, which represent which is given each AST. It will map it to an accumulating value. So it's the scaling factor that we see. And it's formally called a ranked list. And we recurse starting from node ID, which is the right-hand side of that int. And we -1 every time. So we are doing a reverse traversal. And we'll return a state of ranked list to a free vector builder. So in the recursion, we get the AST from the map. We pattern match on it. If it's 0 or basis, we return it. If it's plus, we get the sensitivity and propagate it. And it's the same for multiplication. But for multiplication, we need to scale the sensitivity. And then we recurse. And after we recurse, we have two builders. So we add them together. And finally, we just turn the free vector builder into a free vector, and we are done. And here's some example of automatic differentiation. So suppose we have a deck of following. We can evaluate it. We can also do forward mode AD. So we will start at the bottom, and we will calculate and go up. Or we can go do reverse mode AD. So we will start from up, and we will go to the bottom. And that's a long way. So we invent a DSL, and we use hash constant to solve a problem. Now we do not need to traverse the very large data structure. And now we can implement a neural network. So we call that neural network. It's a program with implicit variable. So we can represent that as an existential type. So every program is itself automatically a neural network. We just set that unit as its weight. So that means it has no implicit parameter. A neural network is compositional. So if we have a neural network of x to y and a neural network of x, we can get a neural network of y. So the weight for neural network of y is the product type of the two weight. And when we evaluate it, we pass the two weight to the function and the argument. With finally tagless approach, we can implement a neural network as an interpreter for simply type lambda calculus. Now we have the weight, which is neural network of view. We can also have sigmoid, or add, or bias. Or we can also scale an input. With those, we can implement a new one. And by composing new one, we can get an XOR function. We can also get a loss, which take an XOR neural network as input. And it will try to evaluate the neural network. And by composing loss and XOR, we get a neural network of type view. And that is a whole neural network. And here's how the topology actually look. So S stands for scale at, which take the two input, multiply them by weight, by some implicit weight, and add the two of them. And N is the neural network, which is scaled at, and then passed through sigmoid. Now I've talked about how to implement neural network. But now we can step back and think, what actually is the derivative of a higher order function? Doesn't derivative only make sense on view? The rest of the talk is going to be somewhat dense, and so don't worry if you can't understand it, but it will be very good if you can. Now the thing is, a language is not suitable for exploring the meaning directly. So we need to create another language which is called NonStandard Term. It's basically the same as STLC. But instead, every view in our program can now refer to an implicit variable, and that variable will be the variable that we are differentiating with respect to. Now we can give a logical relation on a NonStandard term. So for everything except view, it's pretty basic. And for a real number, it's saying that t will evaluate it to a dual number, and the left-hand side is the left-hand side is called original. The right-hand side is called diff. And for every unknown input, diff of x is equal to the denotational semantic of original and the diff of that on x. And note that there are no circular argument in here, because we are using the notational semantic and we leave original to derivative in the mathematical sense. So for example, if we have a logical relation on view to view, if we have a term of view to view, the logical relation of that is give me a dual number with the right-hand side being the derivative of left-hand side, and I will give you a dual number with the right-hand side being the derivative of left-hand side. So this is saying that every term in the language has the dual number property, preserve the dual number property. And now it's slow to carry the closure around. So we can always optimize the non-standard term to standard term. So non-standard term don't actually exist in the implementation. And a logical relation only state that the dual number property is preserved, but we need another logical relation to relate the original term to the term after the derivative. And it's basically nothing tricky there, so I will omit it. But the main theorem is, for every term, the term and the derivative of that term is related, and the derivative of that term has the dual number property. Now, we have formally assigned a meaning of AD in our language using logical relation, operational semantic, and denotational semantic. And here's all the connection between neural network and functional programming and programming language. So the three underlying ones are the ones I haven't talked about in the slide, but they are equally important, so I left them in. And here's some implementation detail. The reference. And it's done. So do you guys have any question? Yeah.
How's the performance of this compared to like a hard-coded?
I have not optimized it for it to run on GPU, but that will be a next step. And that's it.